Morning, dear students. Today, our discussion is equations of equilibrium for a two-dimensional problem. Okay. Yeah. So you see an element here, which is of two-dimensional in nature, because I have taken the plane XY for representing this element. Okay. Yeah. I have represented the right vertical face as 1, left vertical face as 2, the top horizontal face as 3, bottom horizontal face as 4. Okay, these are the faces where the thickness perpendicular to this screen is 1 unit. Okay, so that makes the problem two-dimensional. Okay, yeah, so for generating this equations of equilibrium in a differential form, okay, so other way called as differential equations of equilibrium. Okay, so let us write equilibrium equation in x direction. Sum of x forces is 0. So if you observe how I have represented the stresses on each face, the face 1 has got normal stress sigma x on 1 face 1 and shear stress tau xy. Okay, the opposite face also has got stress in x direction, normal, perpendicular direction, tangential tau xy 2. Okay, shear stress. So similarly, phase 3 will have stress in y direction and tau xy, and phase 4 will have sigma y directional normal stress and tau xy. Okay. Yeah, so let us try apply sum of x forces 0. So what are all x forces are there for us? Let us see. So this is in x direction and this is in x direction. This is also in x direction and this one. So there are 4 stresses and convert them into the forces. Okay. So let us say sigma x of 1 stress into area. This dimension is dy into thickness is 1. This is area. Okay. So this is towards positive direction. I write positive value. And this one is negative. So sigma x of 2 area dy into 1. Okay. Same way, other two forces like this is 1 tau xy on phase 3. The area is this is dx into 1. This is towards positive. Okay. Minus tau xy on phase 4 dx into 1. So these are all the stresses that are acting on the faces. Let us imagine that there is the body force which has got for this element, and the body forces are, let us say, x and y. Okay, so body force, if I write plus x into the volume, okay, dx dy into 1. Okay, so this is the body force. So now we have got total forces. Sum is equal to 0. Okay, right. So now if you take dy common, okay, so it is sigma x on phase 1 minus sigma x on phase 2 multiplied by dy plus tau xy on phase 3 minus tau xy on phase 4 multiplied by dx. Okay, the other one plus x body force dx dy is equal to 0. Okay, so this is sum of x forces 0 equation. Now divide this equation with the area of the element. So divide the above equation with dx dy. Okay, so what you have now is sigma x1, sigma x of 2 dy by dx dy plus tau xy on 3 on 4 into dx divided by dx dy plus x into dx dy divided by dx dy. Okay, yeah, now cancel out the terms. Dy goes here, dx goes here, and both dx dy goes there. Okay, yeah, now this difference I'll write it as like d sigma x, the difference in sigma x values on the 1 and 2, okay, divided by dx plus the difference in tau xy values divided by dy plus x is equal to 0. Okay, so now if you apply the limit, apply limit dx tends to 0 and dy tends to 0, and this will become a 4. Okay, right, as the size of the element you are making this into a point by shrinking this dx into dx tending to 0 and dy tending to 0. Okay, you are making this entire thing as a point. Okay, so in that case mathematically it is going to become partial derivative dou sigma x by dou x dou tau xy by dou y plus x is equal to 0. This is equilibrium equation 1 in differential form. Okay, so similarly if you apply for y direction sigma f y0, okay, you can always get the second equation, that is dou sigma y by dou y dou tau x by dou x plus y body force in y direction is 0. So this is second equilibrium equation. Okay, so these two are called as differential equations of equilibrium, okay, for a two-dimensional problem. Yeah, thank you. We'll see you in the next session.